Good. Welcome to this sub-lecture on application of the Newton backward difference formula. So before I give examples, I'll just use the table that you have done before to explain what you need to know before you apply this formula. So to apply the Newton backward difference formula, just the same way we saw in this table here, that Newton forward, you start at the beginning of the difference table. In a similar manner, Newton backward, you start at the bottom of the difference table. So therefore now, like if you are asked to find the value of, using this table that we have done before, the value of 1.55. You see in this table, 1.55 lies at this point here. Let me just do it. This way I have 1.55. So at that point, 1.55 is near the bottom of the difference table. So therefore now, to get a better approximation by Newton backward difference formula, now you pick a value that is at the bottom of that value now. So pick now 1.6. So this becomes the row that you apply. You pick this one here, and then you move in this way. So this is what you'll be calling now your F naught. This first become backward of F naught, second backward of F naught, third backward of F naught, fourth backward of F naught, fifth backward of F naught. So this is how we apply. Yeah, actually the opposite of what you do in the case of the forward. If now they ask you to find a value like say 1.5, 1.45, so therefore you pick the value below it. So you pick this value here, and then you use this as your value. So this becomes the F naught, this becomes the backward F naught, this becomes the backward second of F naught, this becomes the backward third of F naught, this becomes the backward fourth of F naught, etc. So ideally the opposite of what you do in the forward is what you do in the backward. Similarly, so then now let's now do some examples to illustrate that. So examples on Newton backward interpolation formula. So example 1, find an interpolating polynomial passing through all the following points. So you just want to do the same examples to see how we arrive at the same solution. -1, 0, 1, 2, 0, -1. This was 15. This was 0. So as usual, you draw the difference table. So solution. So X, F, first backward, second backward, and then third backward. So -1, 0, 1, 2. So 0, -1, 0, and then 15. So I remember the way we get the differences is just the same, whether you are drawing forward or backward difference table. So here we have 15, we have 1, we have -1. So this will be 14, this will be 2, and then this becomes 12, just as we have seen in the first case. So these are the differences. So therefore now, because we want to use the backward difference formula, we start at the bottom. So this is the row that we need to start with. So this becomes the row that we need to use. And then once you identify this row, then you pick this diagonal. So therefore now, this becomes our F naught. This becomes the first backward of F naught, second backward of F naught, and then third backward of F naught. So this is how we identify them. Backward difference formula at the bottom. Don't forget that. So therefore, we write f of x is given by f naught plus p backward f naught plus p into p plus 1 second backward of f naught plus p into p plus 1 p plus 2 over 3 factorial third backward f naught. We don't have to write the fourth backward because the values we have doesn't define the fourth difference. So we just stop, the formulas just stop at this point here. So let's identify our F naught. From our table, our F naught is the 15. Then the first backward F naught is 15. Then the second backward of F naught is 14. And then the third backward of F naught from this table is clearly 12. And then let's see what is, remember, don't forget that the relationship between P and X is X equals to X naught plus PH. So you need to have the H. H is the distance between two consecutive X values. So from -1 to 0 is 1 unit, 0 to 1 is 1 unit, 1 to 2 is 1 unit. So therefore H is 1. And then X naught, now X naught is 2 in our table, in our value here. Once this F naught, then this becomes automatically X naught. So X naught is 2. So we replace these values into this formula to get the relationship between X and P. So X will be given by X naught is 2 plus P times 1, which is P. So which means that P is nothing but X minus 2. So therefore, in this formula, where there's P, you replace by X minus 2. So therefore, now we have f of x would be given by f naught. F naught, you have already known its value. So then let's just write f naught then anyway. F naught, which is 15, then plus, where there's P, we put x minus 2 backward f naught plus x minus 2, x minus 2 plus 1 over 2 factorial. Actually, I can replace this just by their respective numbers. So I have 15, and then I have next value is 15 also. Next value is 14, and then plus x minus 2, x minus 2 plus 1, x minus 2 plus 2 over 3 factorial, which is just 6. Actually, I can just write this one as 2. This is just 2 factorial, just 2. And then this is 12. So the next thing is now just to simplify this. So I'll have 2, this is 14, 7, So this is 1, this is 2. So f of x becomes 15 plus 15x minus 30 plus, so here you have 7 into x minus 2, x minus 1, plus, now at this point, so this will be x, so, and then I have 2. So I'll have 2x into x minus 2, x minus 1 for this part here. So therefore, f of x will be given by 15 plus 15x minus 30 plus 7 into x squared minus x minus 2x plus 2 plus 2x into x squared minus x minus 2x plus 2. And then f of x will be, so this is 15x minus 15, this and this, and then plus 7 into x squared minus 3x plus 2 plus 2x into x squared minus 3x plus 2. So can say this is the same as 15x minus 15. Now this bracket and this are the same, so I can say plus x squared minus 3x plus 2 times 7 and then plus 2x. So f of x will be 15x minus 15 plus 7x squared so plus 7x squared, and then minus 21x plus 14 plus 2x cubed minus 6x squared, and then plus 4x. Just opening this bracket. You can always simplify in the whichever way you like it. At the end of the day, you will have the same answer. So I'll have start with the highest power, 2x power 3, and then this, and this gives us positive x squared, and then 15x minus 21, and then 4. So 15 plus 4 is 19. 19 minus 21 is minus 2, minus 2x. And then 14 and minus 15 plus 14 is minus 1. So which is the same result that we got in the previous method. So we get the same thing. And then example 2, using the values in example 2 on Newton forward interpolation formula, find the approximate value of sine 35 degrees. So I'm not going to redraw the table. I'll just go back and refer to it and see how we need to behave. So here is the table, the example 2 that they're referring to. So 35 degrees will be here. This is where you have 35 degrees. Now, to use Newton backward difference table, you start at the bottom of the difference table. Now, because 35 lies between 30 and 40, but 40 is below 30 in this difference table, so therefore 40 becomes the rule to use. So we come here and say, so this is what is going to be our X naught, F naught. This becomes the row that we need to apply. So therefore now this becomes the diagonal that we need to use. So therefore now this becomes our X naught. This is F naught. So this is the backward F naught. And then this becomes the, so this was 0. So 0. For 20 we have 0.34. Then we have 202. So this was 0.17365. So therefore now this becomes the second backward, third, and then this is the fourth backward that we are going to use. So then let's write the formula. So we'll say, so remember that f of x is given by f naught plus f naught plus p backward f naught plus p minus p plus 1 plus p into p plus 1 p plus 2 over 3 factorial. So because now we have up to the fourth difference, so then we need to write up to 4. And then where, don't forget this, that where x is x naught plus ph. Now our x naught for the table is 40. Our x is 35, so x is 35. X naught is 40. And then the mesh spacing from that table is 10. So we have 35 equals to 40 plus 10p. So minus 5 equals to 10p. So p equals to minus 0.5. So therefore, we are going to use now where there's p in the formula, we put negative 0.5, and then we have the values of those differences from the table. So we'll have so f of 35, which is the same as sine of 35, is approximately equals to now when the f naught from our table, this is the f naught, so 0.64279, and then followed by this value as first backward. So we'll have 0.64279 64279 plus negative 0.5 into negative 0.5 plus 1 over 2 factorial just 2, and then multiplied by, it's not just negative 0.5. This, remember, it's p, then first backward. So given by negative 0.5 times 0.14279 plus minus 0.5 into minus 0.5 plus 1 over 2 factorial just the same as 2, negative 0.519 plus negative 0.5 into negative 0.5 plus 1, negative 0.5 plus 2, 3 factorial is 6 times negative 0.0048, then plus negative 0.5 into negative 0.5 plus 1, negative 0.5 plus 2, negative 0.5 plus 3 over 4 factorial, time that difference is 0.000031 from the table. Just refer from the table that you have done before. And then when you work out this, you get 0.64279 minus 0.071395 plus 0.00189875 plus 0.0003 minus 0.000012109375. So that will give you 0.573586164. You can now, from this is an approximation of sine of 35 degrees. So you can always now work out the error. So error or the transition error will be simply given by what you key in as sine 35 degrees in the calculator minus this approximation. And you can always now go ahead and get relative error and then percentage error. Or if they had specified that approximate sine 35 degrees using a polynomial of degree 3, then you will stop at the third difference, and therefore the error becomes that term in the fourth difference. So transition error will be given by negative 0.000121099375. So this becomes the transition error if we are approximating by a polynomial of degree 3. So the fourth term becomes the transition error. So do as many examples as possible on the same, on how to apply Newton forward and Newton backward. And just remember that when the value you want to find its approximation is near the beginning of the difference table, you use Newton forward interpolation formula. But when the value of x that you want to approximate is near the bottom of the difference table, then you use Newton backward difference formula. But then the question will be now, when the value you want to approximate is at the bottom of the difference table, so which formula do you apply? So like, for example, in this table here, Like for example, this table here. So like if you have to approximate, say, a value like 1.35. So if you want to approximate the value of 1.35, 1.35 is at the middle of the table. So when you use Newton forward and Newton backward, they will not give a better approximation. What the answer you'll get will be far away from the true value. So to approximate a value which is at the bottom of the difference table, then we use these other formulas, which we are not going to discuss here, but find some time to read about them and then do some examples in the textbook that we have referred you as our reference book. So there's what we call the Bessel's formula. We have Everett's formula. And then we have another method called Starling's formula. Yes, Starling's formula. So this is an assignment. So go to the reference book that we have, that is already available in the SOMAS, and then read about Bessel's, Everett's, and Starling's formula, and then do some examples on the same. How these formulas are applied, and they applied when you want to approximate the value which is at the middle of the difference table. Is when these formulas becomes very useful. But when the value you want to approximate is near the bottom, then you use Newton backward difference formula. When it is near the beginning of the table, then you use the Newton forward difference formula. So thank you and have a good day. Next time we meet, we'll be discussing about numerical differentiation. And before we meet for that class, ensure that you have understood how to derive both the Newton forward and the Newton backward difference formula. Thank you and have a good day.